Okay, guys, this is the December benchmark review. Remember, in order to get credit, you have to write everything that we write. There will be a series of videos. It will not be able to be done in just one video. So after you watch this first one, you'll need to watch the other ones. This is a test grade. It is due on Wednesday, December the 11th. And if you get your parent's signature on the top, you will get 10 extra credit points. Please make sure that you complete this. It's getting you ready for your benchmark, which will be Wednesday the 11th and Thursday the 12th. And remember, if you do your benchmark, if you get a master's on your benchmark, you will receive an A in this class for the 9 weeks, and you will be exempt from our final exam for the semester that will be taking place the week before we get out for the winter break. So, number 1, tug of war. Each student on team 1 pulls with a magnitude of 20 newtons. So, team 1 is right here. That means each student is pulling with a force of 20 newtons back towards the left. Team 2 is winning, so that means that the team 2 must have a greater force because they're winning. As each student pulls with a magnitude of only 16 newtons to the to the right. So calculate the net total force for the winning team. Well, the winning team is team 1. All we have to do is add these 4 together. 16 plus 16 is 32. So the total Newton force would be 64 newtons. The game of tug of war is an example of unbalanced forces. That's when one force is bigger than the other. Obviously, we can even double check that. This one would have a net force of 60 newtons. This one was 64 newtons, and so this one would be our winner. Number 2, what is required to change the direction of a moving object? Change. We told you guys, change always causes acceleration. That's when something changes, and the only way to accelerate or change motion is with unbalanced forces. If forces are balanced, there will be no change in motion. So A, an unbalanced net force on the object. That looks correct, but we want to check the rest of them. B, a balanced net force on the object. Nope, that would cause no change in motion. Several forces acting in the same direction. Well, several forces acting in the same direction may or may not cause a change. We don't know if they're balanced or unbalanced. And no force, there are always forces. Always forces acting on objects. Okay, examine the diagram below. If the net force acting on the box, is 10 newtons to the right, what is the force on arrow X toward the left? So we're looking for this unknown force right here. Report your answer in the grid below. So we want a net force of 10 newtons to the right. That means that these combined forces have to be 10 newtons bigger or more, greater than these combined forces. Well, these combined forces, we have 21 plus 11, gives us a combined force of 32 newtons to the right. Right here, we only have 8 newtons that we know of, plus what number is going to get us to a number that would leave us with 10. So that means 32 minus this number right here needs to equal 10. So 32 minus what number equals 10? It would be 22. So this number right here has to be 22. What number do we add to 8 to get to 22? It would be 14. The only way to get to 22 on this side would be to make this 14. Because 8 plus 14 is 22, and 11 plus 21 is 32, leaving us with a net force of 10. So if we want 14, we're going to put it in the grid over here. We put it in front of the decimal. This gridables have gotten you guys a lot this year, so please be careful with your gridding. The 4 has to go in front of the decimal because it is a whole number. And then, of course, you grid the 1, and you bubble the 1 and the 4. Number 4, what calculating net force? If the arrows are pointing in the same direction, then you do what? When. Sorry, that says what. It should be when. When calculating net force, if the arrows are pointing in the same direction, then you add. we add in the same direction. If they are pointing in the opposite direction, then you are going to subtract. Okay, for number 5 through 10, these are vocabulary words. Actually, it's 5, 6, 7, 8, 9, 10, 11, I believe. Inertia, mass, acceleration, velocity, speed, force. For those words, you will need to look them up and define them in your own words. We're not going to do that for you, because you can look these words up, look them, use your journal, use your resources, and then you need to put them in your own words, the definitions. So please make sure that you get those done on your own. Okay, number 11. Identify the action-reaction forces in a rocket ship blast off. All right, so here we have our rocket ship, and of course it has, here's the Earth, and the thrust is going to push down. That is the action. The thrust coming out of the rocket is the action force. It's going to push down on the Earth. And the Earth pushing back up is the reaction force. So the thrust of the rocket down is the action. And the Earth pushing up is the reaction. All right, describe how inertia and mass are related. All right, well, we talked about, usually we use soccer ball and bowling ball. Inertia is the tendency of an object to resist a change in motion. We like to call it how stubborn an object is. It doesn't want to move if it's at rest, or if it's moving, it doesn't want to stop. And the more mass it has, the more inertia it has. So more mass equals more inertia. That's why a bowling ball has more inertia than a soccer ball. A bowling ball has more inertia than a soccer ball. So if a bowling ball is in motion, it's going to take a lot more force to stop it than a soccer ball. If we want to move the bowling ball and a soccer ball, it takes more force to move the bowling ball, so it has more inertia. Number 13, describe the relationship between the mass, the force, and the acceleration of an object. Explain the laws below and give an example of each. Okay, so if we have, again, let's talk about the bowling ball. Here's our bowling ball. And we have a soccer ball. Here's our soccer ball. I'm not going to draw the designs on the soccer ball. And we apply the same force. So let's say 5 newtons of force to both of them. They're the different masses. Obviously, this one has more mass. Then this one, the soccer ball, will have greater acceleration. More mass means less mass means greater acceleration. So these are what are called inversely related. So more mass means less acceleration. Now, on the other hand, if we have the two of the same objects, let's say we have 2 bowling balls, they have the same mass, and we apply a large force, so 100 newtons, and a very small force to the other one, 10 newtons, then the large force will have greater acceleration. And this is all about Newton's. This is what Newton's second law, the law of acceleration, explains. Greater force right here causes more acceleration. Over here we have more mass, which will cause less acceleration. It's very much common sense stuff, guys. Okay, the first law of motion, this states that an object at rest or in motion remains unless acted on by an outside or unbalanced force. An object at rest or in motion remains that way, remains at rest or in motion, unless acted on by an outside force. This is a seatbelt, perfect example. So we have somebody driving in a car, pardon my drawing, and the car is moving, the person is moving, keeps going. If the car suddenly stops because it hits something, well, the person is going to continue moving and fly until eventually the ground stops them. The second law of motion, that is the law of acceleration. That's the one that we just talked about. That states that if we have two objects, let's like the shopping cart as an example. So here's our shopping cart, and this shopping cart is empty versus a full shopping cart. Please pardon my drawing, although I'm not an artist. And this one is full of stuff. This one has more mass. If we apply the same force, say 10 newtons, to the empty one will have greater acceleration, and this one will have less acceleration if the forces are the same. Now let's take our two shopping carts and let's pretend they are both empty. They are both the same mass, and we apply a big force to this one and a smaller force to this one. The big force is going to have a greater acceleration. Okay, so it's kind of two parts. We're going to separate these two. Separate them. This first part is dealing with two different masses, same force. And then the second part is the two same masses but different forces. And finally, the third law. Third law is all about the action-reaction. So this is why if we are in a rowboat and we are rowing, okay, this is our water here, and if we want to move this way, then we have to paddle with our paddle here this way. So if we push back on the water, then we move forward. Because as we push back, then the water pushes forward on us. Same goes with the rocket, which is the one that we use a lot. Okay, the rocket pushes down on the Earth. And what does the Earth do? The Earth pushes back with the same amount of force, allowing the rocket to lift up off of the ground. So this is action, reaction. So in the case of the swimming, then the pushing back is the action force, and us moving forward is the reaction. It's the water pushing us forward. The rocket pushing down on the Earth is the action. The Earth pushing up is the reaction. In baseball, let's say we have a baseball bat, and we have the baseball that is coming at the baseball bat. When the baseball bat hits when the ball hits the bat, then the ball pushing this way on the bat would be the action, and the bat pushing back onto the ball would be the reaction. Sorry, reaction.